Have you ever wondered how the deeply complex AI that lives in massive, energy-hungry data centers somehow makes its way onto your smartphone without completely draining your battery in 5 minutes? Well, today, in this explainer, we're diving into a groundbreaking paper by Jeffrey Hinton, Oriol Vignoles, and Jeff Dean that answers exactly that. We're going to explore how we can actually distill the vast knowledge of a giant neural network into something incredibly small and lightning fast. To understand why this is necessary, we have to start by looking at a massive computing bottleneck. You see, training an AI and actually deploying it out in the real world are two completely different beasts. Imagine millions of users needing to query a voice assistant or an image classifier at the exact same moment. If we tried to deploy the giant, power-hungry models we use in the lab directly to all those users, the computational cost would be just astronomical, and the lag time would make it completely unusable. The divide here is pretty stark. During the training phase, the whole goal is to extract deep, complex structure from absolutely massive, highly redundant datasets. Real-time speed? It really doesn't matter. We can just let clusters of GPUs run for weeks on end. But once that model hits the deployment stage, the rules change entirely. We face incredibly stringent requirements on latency, meaning it needs to answer us instantly. And there are strict limits on memory and computational resources. It simply doesn't make any sense to use the exact same architecture for both of these vastly different jobs.
The researchers use this absolutely brilliant biological analogy to explain this concept. They point out that many insects have a larval form, right? Think of a caterpillar. It's highly optimized for just sitting there, extracting energy and nutrients from its environment. It basically just eats and grows. But eventually, it transforms into a completely different adult form, a butterfly, which is optimized for the entirely different requirements of traveling and reproducing. In large-scale machine learning, our AI shouldn't be the same in its training and deployment phases either.
To do all that heavy lifting during learning, we need what the authors call a cumbersome model. This is our caterpillar. It could be a massively large neural network or even an ensemble of many separately trained models whose predictions all get averaged together. This cumbersome model is heavily regularized, wildly complex, and optimized purely for extracting structure from data, without a single concern for real-time speed. It learns incredibly deeply, but it is way too slow and heavy to actually put in the hands of a user. So, here's the million-dollar question. How do we take that heavy, cumbersome model and squeeze it into a small, fast model that's actually suitable for deployment? This is the core concept of knowledge distillation. But it's tricky. How do you transfer knowledge from a huge model to a tiny one? A lot of people think of an AI's knowledge simply as its specific parameter weights, but you obviously can't just cram 1,000,000 weights into 1,000 slots. The secret to making this work is that we have to change how we view that knowledge entirely. The solution lies in how we view the training targets. Usually, we train models with what we call hard targets, meaning an image is 100% a BMW, 0% a garbage truck, and 0% a carrot. But a fully trained, cumbersome model actually assigns tiny probabilities to incorrect answers, which we call soft targets. Sure, it knows the image is a BMW, but it might say there's a 0.001% chance it's a garbage truck and a 0.0000001% chance it's a carrot. Why does that matter? Because mistaking a BMW for a garbage truck is still exponentially more probable than mistaking it for a carrot. These tiny ratios reveal the hidden similarities between classes. They literally show us how the massive model actually generalizes and understands the world around it.
When we use these soft targets to train our smaller, deployed model, the benefits are huge. First off, it reflects the true generalization of the cumbersome model. We aren't just telling the small model the right answer, we're teaching it how the large model thinks. Because the soft targets have higher entropy, meaning those probabilities are spread out to reveal more nuance, they contain vastly more information per training case than a simple true or false hard target. There is less variance in the gradient during training, which practically means the smaller model can be trained on much less data. And we can use a significantly higher learning rate without the whole thing crashing. It's just a wildly efficient way to learn.
But we do run into a slight mathematical hurdle here. In tasks where the cumbersome model is highly confident, those probabilities for the incorrect answers are microscopically small. We're talking so small that they have almost zero influence on the cost function during training. To fix this, the researchers introduced the concept of temperature, denoted by the letter T, into the final softmax layer of the neural network. Now, normally, in standard AI training, this temperature is just set to 1.
But during the transfer process, we artificially crank up this temperature T. By turning up the heat, so to speak, we essentially soften the probability distribution produced by the cumbersome model. Those microscopic probabilities get boosted, forcing the massive model to loudly reveal all those hidden similarities and rich structures over the data. We then use this exact same high temperature when training the small model to match these soft targets. And once the small model is fully trained, we just drop its temperature back down to 1 for the real world.
Let's put some numbers to this and look at some real-world proof applied to a state-of-the-art automatic speech recognition system. The baseline single model they started with had a word error rate of 10.9%. By building a huge, cumbersome ensemble of 10 massive models, they squeezed that error rate down to 10.7%. But running 10 models for every single voice query is obviously way too expensive. So they distilled the knowledge from all 10 models into one single, small, distilled model. And the result? The distilled single model perfectly matches the 10.7% error rate of the massive ensemble. It captured all that performance, but in a totally deployable package.
To really prove how much rich information is embedded in these soft targets, the researchers ran this fascinating experiment using the famous MDIS dataset of handwritten digits. First, they trained a massive, cumbersome model on all the digits 0 through 9. But when it came time to distill that knowledge into the smaller model, they did something kind of crazy. They completely removed all images of the number 3 from the transfer set. From the perspective of the small distilled model, the digit 3 is a mythical creature. It has literally never seen one. And the results? Honestly, they're mind-blowing. When they tested this small model and finally presented it with the number 3, it achieved a 98.6% accuracy rate. Just let that sink in for a second. It correctly identified almost every single 3 it was shown, despite never seeing one during training. How is that even possible? It's because the soft targets of all the other digits, like the 2s, 7s, and 8s, contain so much rich similarity structure from the big model that it perfectly sculpted the small model's understanding of what a 3 must look like. It left a perfect negative space for this mythical digit.
So, we know this distillation process works wonders, but what happens when you hit a wall, the absolute limits of scale? The researchers pivoted to an internal Google dataset called JFT, which contains a staggering 100 million labeled images across 15,000 different categories. A dataset this massive takes a single huge model months to train, even across multiple cores. It is simply impossible to train an ensemble of 10 of these massive models. It would literally take years. So, how do we get the benefits of an ensemble without the impossible compute time?
The answer is surprisingly simple: divide and conquer, using generalist and specialist models. Think of it like a Swiss Army knife versus a scalpel. Instead of trying to train multiple massive models on absolutely everything, we train one cumbersome generalist model on all the data. That's our Swiss Army knife. Then we train many smaller specialist models, our scalpels. Each specialist starts with the generalist weights, but then it's trained intensely only on highly confusable subsets of classes.
For instance, they ran a clustering algorithm to find out exactly what the generalist model got confused by the most. One cluster turned out to be all about bridges, suspension bridges, viaducts, cable-stayed bridges. Another cluster was entirely specific makes and models of cars. A specialist model is assigned to just one of these clusters. It basically lumps everything else in the entire world into a single dustbin class and focuses all its learning power purely on becoming an absolute expert at telling an Opel Astra apart from a Mazda Familia. Because they focus on such a tiny subset, these specialists can be trained completely independently and extremely fast.
When it's actually running in the real world, they use an incredibly elegant two-step inference process. Step 1, an image comes in and the generalist model looks at it to find the most probable broad classes. It might say, okay, I'm pretty sure this is a car. Step 2, the system then wakes up only the specific active specialist models that actually cover cars. The car specialist looks at the image and refines the probability distribution, confirming exactly what type of car it is. The beauty of this approach is in the scaling. If an image triggers just one specialist model, the relative accuracy improves by 3.4% over the baseline. But because these specialists are small and independent, you can easily have overlapping specialists working at the same time. If an image is evaluated by 10 or more specialists at once, that relative accuracy improvement skyrockets by 14.1%. You get the raw power of a massive ensemble, but because training specialists is so easily parallelized, it takes a fraction of the time.
Before we finish up, I have to mention one more superpower of knowledge distillation: regularization. The researchers wanted to see just how much helpful generalizing information is truly carried in these soft targets. So they took that massive speech recognition model we discussed earlier, and they tried to train a brand new model using only 3% of the original training data.
The results were a total validation of the whole concept. When they tried to train on just 3% of the data using standard hard targets, the model severely overfit and crashed out at just 44.5% accuracy. It just didn't have enough data to learn the real patterns. But when they used the soft targets provided by the cumbersome model on that exact same tiny 3% dataset, the new model hit 57.0% accuracy. It almost reached the performance of a model trained on 100% of the data. Soft targets are just an incredibly robust way of communicating deep, underlying regularities from a massive model to a smaller one, actively preventing it from overfitting.
And that brings us to the ultimate takeaway of this explainer. The researchers poetically call these hidden probabilities the dark knowledge of an AI. By softening the probability distributions, we can illuminate this dark knowledge and distill the power of massive, room-sized computing clusters into models small enough to run instantly on your phone. It completely changes how we view AI deployment. If we can seamlessly transfer the incredible generalization ability of our heaviest models into lightning-fast, everyday applications, we really have to ask ourselves, what are the true limits of the AI we'll soon carry in our pockets? It's a thrilling question to leave you with. Thanks for joining me on this deep dive, and keep learning.